Hi, I'm Schrammel and I'm presenting the paper Jenny, which is about securing Syscalls for protection key-based memory isolation systems. Protection keys for Userspace allow efficient intra-process isolation on a fine granularity. A few examples of such sandboxes are Arim, Hoda, or Donkey. However, these systems often do not sufficiently filter Syscalls, and they also use very slow mechanisms or rely on custom hardware to do so. In this paper, we analyze the Syscall interface for potential problems, then we define filter rules for different PKU sandboxes. We also analyzed Syscall interception mechanisms, and on top of the Donkey's framework, we then implemented same-thread Syscall filtering, nested Syscall filtering, and safe signal handling. With protection keys for Userspace, memory pages are tagged with a so-called protection key. The key is then stored in the page table entry. On Intel CPUs, these keys are 4-bit wide, so 16 keys exist in total. The PKU register contains read and write permissions for each of these keys. This allows for quick permission changes in the user space. However, for use in a sandbox, one has to safeguard this register. That means no unsafe instructions exist that may write to the register, and also syscalls that may bypass this mechanism need to be blocked as well. In a PKU setting, we typically have a number of different protection domains within a single process, as well as an in-process monitor. Donkey's non-standard hardware extension delivered syscalls directly to the monitor before entering the kernel. However, on off-the-shelf CPUs this doesn't work. Instead, syscalls get delivered to the kernel where they must be handled. However, the kernel is not aware of these user space domains. Moving complex filtering logic to the kernel would increase the kernel's attack surface. Alternatively, we can dispatch the syscalls back to the monitor, but this introduces additional context switches. Furthermore, we might have nested domains which also want to filter their respective child domains. In short, there are a number of challenges such as the need for an efficient mechanism, effective filters, the kernel not being aware of user space domains, nested domains, signals, and so on. Existing work by Connor et al. Showed some Syscall-based attacks on PKU systems. For example, via indirect memory accesses via the procfs and other syscalls like process VM write or ptrace, mutably backed read-only memory, seccomp filters, signal handlers, which currently must run on an unprotected stack, which leaves them vulnerable to attacks. So by systematically analyzing the kernel interface, we found many more syscalls that must be filtered. For example, the madvise syscall, which is typically used to improve performance by giving the kernel additional memory information. However, an attacker can use it to clear pages irrespective of their protection keys. Break and sbreak, typically used for managing heap memory, but it can be used to clear pages and even remove protection keys. Userfaultfd can be used to handle page faults in user space, but it allows to write arbitrary values to protected memory pages. The personality syscalls can be used to make future mappings executable, which negates the write XOR execute policy for PKU sandboxes. Also, core dumps can cause information leakage for PKU sandboxes. In the paper, we describe many more pitfalls. Based on our Syscall analysis, we derive 3 sets of filter rules for PKU sandbox. First, we define base Donkey, where we assume Donkey's custom hardware to present, which protects the PKU register from being written to. There, we filter any syscalls to ensure memory isolation, safe signal handling, and other application resources. On top of that, we define base x86, which additionally prevents exploitation from unsafe instructions. Also, any executable mapping is scanned and made immutable. Finally, we define local storage, which handles any file-based syscalls to allow for a per-domain file system and domain-private file descriptors. We protect the memory on multiple layers. First, memory itself, by protecting it with protection keys. Second, we protect the memory mapping, such that its permissions and keys cannot be changed. Third, on disk, if a mapping is file-backed, and also any aliases, such as shared memory or symbolic links. For efficiency reasons, we disable the procfs and the creation of core dumps to avoid scanning file paths. To enforce our filters and accommodate for our features, the underlying filtering mechanism must fulfill several requirements. For example, it must be able to delegate the syscall to the user space monitor. It must be domain aware to a certain degree, such that trusted domains like the monitor are not filtered. It must also allow for complex filters that may manipulate arguments or even replace them with different syscalls. We also need the ability to impersonate other domains. For example, When a parent domain filters a syscall for a child domain, it should be able to execute syscalls on behalf of that filtered domain. Furthermore, hierarchical domains must be supported as well. And finally, it should not be too expensive. We analyzed the filtering mechanisms that exist in Linux today, like ptrace, seccomp, and so on. However, we found that none of them really fit our needs. For example, they are not domain aware, rely on insecure signal handlers, are too limited, too slow, or not available on common CPUs. So, we designed our own mechanism and implemented it as a kernel module. We selectively intercept syscalls only if necessary and delegate them to the Userspace monitor. For evaluation purposes, we also added another mechanism where we modified the libc to dispatch syscalls to the monitor. This approximates the performance of Donkey's hardware extension for x86. Now let's move on to signals. Previously, I mentioned signal handlers could not be used securely in a PKU sandbox because they could not run on protected stacks. So we propose a small kernel patch to change this behavior. And we provide an API such that domains can register syscall handlers and filter or virtualize signals for child domains. For nesting, we allow parent domains to run filter code before and after syscall. If there are more nesting layers, the syscalls are handled as shown here. In the paper, we go into detail about many other design aspects, such as why we want to have same thread filtering and how to achieve it, even with ptrace, and also how to securely design filters that are free from time of check to time of use vulnerabilities, and so on. We also designed a new PKRU call gate that is thread safe and allows for multiple domains. Now let's talk about some performance numbers. Here we use Jenny to sandbox a wide range of existing applications with different filtering mechanisms and filter sets. For local storage, shown in yellow, we can see some slowdown for file-heavy applications like Git. However, the other filter sets, which will be used in practice, shown in blue and green, show a negligible overhead for most applications, especially when using our PKU user delegate mechanism. You can also see that our PKU user delegate mechanism is much faster than the other mechanisms. This is because we only delegate syscalls back to the monitor when they are potentially unsafe or when a parent domain wants to filter them. To conclude, through systematic investigation of the syscall interface, we found several new attack vectors, based on which we derived efficient filter rules. We studied existing and designed new syscall interposition techniques for PKU sandboxes. We allow for domain-specific syscall filtering and secure signal handling. And we showed that PKU-based sandboxing can still be practical even when properly secured. Thank you for your attention.